Today we are studying Sturm's conoid and spherical equivalent. We will be discussing the concepts right from the basics and going to the advanced. Before we go into the details of the Sturm's conoid, it is very important for us to know what is meant by a toric surface. A perfect spherical surface as shown over here will have equal refractive powers along all the meridian. That means the 90 degrees meridian and even the 180 degree meridian or any other meridian if you take, all of them will be equally curved and all of them will have equal refractive power. However, if we take a surface like this, which is shown over here, it does not look like a perfect sphere. However, it is looking as if the perfect sphere has been compressed from the either side in such a way that the vertical meridian has become now more curved compared to the horizontal meridian. Such a surface in which the meridians which are aligned at 90 degrees to each other are not equal and one of the meridian is having more power compared to the other meridian. Or what I mean to say is one meridian is more curved compared to the other meridian. Such a surface is called a toric surface. When the light rays pass through a perfect spherical surface as shown over here, what happens is that all the rays will actually come to a point focus because the power of all the meridians is same and all the meridians are equally curved and therefore they will equally refract and bring the rays to a focus, to a single focal point, and this is called a point focus. However, the refraction of the light rays is totally different in case of a toric surface. In case of a toric surface as shown over here, the vertical meridian is having more power compared to the horizontal meridian. Therefore, the rays of light will get convergent or they will get to a focus sooner from the vertical meridian compared to the horizontal meridian. That means if the rays are passing like this, the vertical meridian will focus them at a point, say A. The horizontal meridian, however, are going to focus them at a point B, which is far from the point A, right? And why does this happen? Because the horizontal meridian is having less power compared to the vertical meridian. So whenever there's a difference in the powers of the meridian, there will not be a single focus as what we saw in a spherical surface. Instead, we are actually having two focus. Now, if we draw two planes, one passing through A and another passing through B, okay, so A and B will be two focal planes. So what do we get to know now? That in a toric surface, two meridians are not having equal power. One meridian is having greater power compared to the other meridian, because of which we have two focal points and we have two focal planes. So when we are studying the configuration of the rays as they are passing through this toric surface, okay, so as we are studying how these rays, when they pass through a toric surface, how will they get refracted, how will they form two foci, at every point of their journey, what will be the configuration of the rays as they are passing through the toric surface, we are actually studying nothing but the Sturm's conoid. So this is the definition of Sturm's conoid, that Sturm's conoid is nothing but it is the configuration of rays refracted through a toric surface. Consider this to be our toric surface, and in this toric surface the vertical meridian is more curved compared to the horizontal meridian. So we can see that the vertical meridian is getting focused at a point much earlier compared to the horizontal meridian. Next, what we'll do is we'll pass a ray of light or a point source of light through this toric surface, and now we are going to observe what will happen when the ray of light will pass through this surface at every individual point. Now let us imagine that we are standing behind this toric surface at a point A. So what will be the shape of that point source of light that we have projected into this toric surface? The shape will be actually an oblate ellipse. And why is that so? At this point A, the vertical rays are actually more converging compared to the horizontal rays, right? So the vertical rays are more converging compared to the horizontal rays. Now because of that, the same point source of light, it will look as if it is compressed. It is more converged from the vertical side, and from the horizontal side, it is actually elongated. That is the reason we are seeing this shape, and the shape is an oblate ellipse. Now let us imagine that we are standing at a point B. Okay, now at this point B, the vertical rays have totally converged. However, the horizontal rays are still converging. So what is happening to this oblate ellipse? That means the vertical, it is as if you are compressing it further, but horizontally, it is not yet that much compressed. So we are going to get a horizontal line at the point B because the vertical rays have totally converged at point B. Now imagine that we are standing at this point C. Now what is happening at point C? At point C, the vertical lines which actually converged at point B, now they have started to diverge. Okay, that means this horizontal line will now start opening. However, what is happening to the horizontal line? The horizontal lines are still converging, but they are a little bit better converging compared to the point B. So what are we going to get at this point? We will get an oval. Okay, and since this oval is more horizontal in shape, this is called horizontal oval. Now let us imagine that we are standing at a point D. Now at this point, what happens is the divergence of this vertical rays will actually become equal to the convergence of the horizontal meridian. So what we are going to get is we are going to get a perfect circle, and this perfect circle where the convergence and divergence of both the meridian is equal is called the circle of least. Now what I mean to tell you is that in an astigmatic surface we actually do not get a single point focus. So the crisp and clarity of an image will not be present in case of a toric surface. However, there will be a point, that is a point D represented in this diagram, where this confusion will be least. Okay, where we can actually get the maximum clarity. Although it is not perfect, there will be maximum clarity because of the circle of least confusion, because these meridians will not, although they are not equal in power at a particular point, that is D over here, their convergence and divergence will become equal, and they might act as if they are similar, although they are not similar. So such a point is called the circle of least confusion. And if this circle of least confusion is present on the retina, the patient will still have a better vision compared to the points A, B, C. Okay, so what I mean to say is if this A, B, C were present on the retina, the patient will still have a bad vision. However, if somehow this point D, that is the circle of least confusion, comes onto the retina of the patient, the astigmatic patient also will have good vision. Now let us see what happens if our retina was present at point E. Now at this point E, we can see that the convergence has increased and the divergence has increased. So what I mean to say is that these horizontal meridian is actually now coming close together, but the vertical meridian is now going far together. So what we are going to get now is actually a horizontal oval. Okay, so we're getting a horizontal oval. Why? Because the vertical meridian is now diverging and the horizontal meridian is now converging. So we are going to get a vertical oval. Now what will happen if we actually stand at a point F? Now at the point F, what is happening to the horizontal meridian lines? The horizontal meridian lines are totally meeting with each other, whereas the vertical meridian lines are still diverging. So what are we going to get? We will get a straight vertical line at the point F. Okay, because the vertical rays are diverging. Now let us stand at this point G over here. So what is happening at point G? Both the horizontal and the vertical lines are now diverging. So finally what we are going to get is, we are going to get actually a prolate ellipse. Okay, so just remember that in the beginning we were actually getting a oblate ellipse, and then slowly it kept on changing from to horizontal line, horizontal oval, circle of least confusion, vertical oval, vertical line, and finally we got the prolate ellipse. So this was the journey of our point light source passing through the toric surface, becoming an oblate ellipse at point A, horizontal line at point B, horizontal oval at point C, perfect circle at point D, and then vertically oval, vertical line, and then prolate ellipse at point G. So there are 2 points at which there was actually convergence of the rays. So the first point was at B where the vertical rays were converging, and then there was a point F where the horizontal rays were converging. So from the point B we got a horizontal line, and from the point F we got a vertical line. So if you observe carefully, nowhere we got any point focus. Instead we are getting focal lines, and these focal lines are our horizontal focal line and the vertical focal lines, right? And it can also be called the anterior focal line and the posterior focal line. So the focal line at B will be your anterior focal line, okay, which is being formed from the vertical meridian because it is converging before, and the F will actually be forming the vertical focal, the second focal line or the posterior focal line because of the convergence of the horizontal rays. Now this is actually showing you the exact configuration of that journey that the light rays were taking, and that journey is nothing but the Sturm's conoid. So we were getting horizontal spheres like this, and then we got the anterior focal line, then we got the circle of least confusion, and from there it started becoming more vertical. We got the posterior vertical line or the posterior focal line, and finally we got the prolate ellipse, right? So now the difference or the distance between the anterior focal line and the posterior focal line is called the Sturm's interval, right? And this entire thing is called the Sturm's conoid. Now, based on the Sturm's conoid, can we tell about what type of astigmatism is present or not? Yes, we can, okay? And this concept is very important. Now, let us imagine an eye where the retina is actually present at a point A, okay? And if you remember, at point A, we were actually getting our prolate eclipse, right? So now, what type of astigmatism this patient has? Okay, the type of astigmatism depends upon where the images are actually formed from both the meridians, right? So here we saw that the vertical meridian was forming the image at the point B and the horizontal was actually converging at a point F. Now, if we are having the retina at the point A, where are these focal lines present? B and F. B and F both are present behind the retina. And we know that the hypermetropes will form the images behind the retina, right? And since both the meridians are forming the images behind the retina, this is nothing but this is a case of compound hypermetropic astigmatism. Now, if the retina was actually present at the point, say B, okay? So if the retina is actually present at our point B, so here. Now, where are the focal lines present and what type of astigmatism it is? We can see that one focal line is directly present on the retina and the other is present behind this retina. So what type of astigmatism is this? This is simple hypermetropic astigmatism. Now, what if the retina was actually present at a point, say, C or at a point, say, D? Okay, any of these points. Now, where are the focal points which are present? One focal point is in front of the retina, that means it is myopic, and the other focal point is actually behind the retina, that means it is hypermetropic. So such a type of astigmatism, it is called mixed astigmatism. Similarly, if the retina is present at a point E, at this point also we are going to get mixed astigmatism. Now, if the retina was actually present at the point F, now what type of astigmatism it is? In this astigmatism, one focal line is directly present on the retina. And where is the other focal line? The other focal line is actually in front of the retina. That means the other focal line is myopic. So what type of astigmatism will this be? This is simple myopic astigmatism. In the end, let us now place the retina at this point, that is G. Now, where are the focal points? Both the focal points are present in front of the retina. So this is a case of compound myopic astigmatism. So this is why Sturm's conoid is so important. The configuration of these focal points, where these focal points are present, and what is the configuration of the bundle of light which is passing through the storic surface is important. Because through this, we can actually know what are the types of astigmatism and the concept behind the types of astigmatism. And through this, we also know the concept of spherical equivalent. Okay, so let us see what is meant by spherical equivalent.